This is an RNZ podcast.
Kia ora, and welcome to episode 45 of Elemental from RNZ. I'm Allan Blackman from the Auckland University of Technology.
And I'm Alison Ballance from RNZ. And we together are alphabetically visiting all the elements on the periodic table, no matter how obscure. Aren't we, Alan?
Oh yes, obscure, that's our middle name. And you could certainly say that today's element is extremely obscure.
Well, it's certainly obscure enough that I've gone my entire life so far without knowing about it at all, which is clearly a state of affairs you are about to remedy for me. Please.
I will certainly try. So lutetium, this is the element of today, and it is named from Lutetia, which is the Roman name for a certain small town which later grew to be Paris.
Ah, merde. I didn't realise we could have been dropping French words into this episode. Tell me more about this little-known Parisian, s'il vous plaît.
Oh, tu, please. Not vous. Oh. Come on. So, lutetium, chemical symbol Lu, atomic number 71, and that puts it smack bang in the lanthanoids, and year of discovery 1907. What's interesting about it? Okay, it was in fact the last of the lanthanoid elements to be discovered. And because we have talked about quite a few lanthanoid elements in Elemental, you will probably be guessing that its path to discovery and isolation is long and tortured, and you'd be absolutely right. It was independently discovered in fact, 1907 by three separate chemists. So there's a French scientist, Georges Urbain, an Austrian mineralogist, Baron Karl Auer von Felsbach, and an American chemist, Charles James. And they found it as an impurity in a mineral called ytterbia. And people thought this mineral consisted entirely of ytterbium, but that wasn't in fact the case. So Charles James bowed out, but the other two scientists proposed different names for the two elements, ytterbium and this new element that required a name. So Urbain chose neo-ytterbium and lutetium with a C, whereas Felsbach chose aldebaranium and cassiopium. And any astronomers listening will know that I have badly pronounced the names of two stars, Aldebaran and Cassiopeia. So a couple of years later, the International Commission on Atomic Weights, which back then was responsible for the attribution of new element names, settled the dispute by granting priority to Urbain and adopting his names, albeit with a slight change. So neo-ytterbium became ytterbium, and much later, lutetium, which was spelt with a C, Lutecium, they changed to Lutetium. Lutetium became lutetium.
Good Lord, so much scrapping over something so obscure. Mm-hmm. And obscure is also a reasonable word to describe exactly where it ought to be on the periodic table, right?
Yeah, indeed. A few episodes ago, you may remember we talked about lanthanum and the fact that it was still a question as to whether lanthanum was part of the lanthanoids or whether it was part of group 3 of the periodic table. And the same argument applies with lutetium with respect to its position in the periodic table. So the reason for this is that lutetium occurs supposedly right at the end of the lanthanoids, and that means it's got a full F shell. It's got 14 F electrons. However, it's also got a single D electron, and that, in some people's opinion, would make it more a transition metal and therefore in group 3 rather than a lanthanoid. But if you look at the way that it behaves chemically, it does behave most definitely like a lanthanoid, and so you will normally find lutetium at the end of the lanthanoid section at the bottom of the periodic table.
Well, that's something I don't have an opinion on. I'm going to let you chemists fight it out amongst yourself.
Fair enough.
Can we actually use lutetium for anything?
We can use it for a few things. I wouldn't say it's one of the more vital elements on the periodic table. Many of its uses are medical, or certainly many of its important uses anyway. And so we use one of its compounds in PET scans. So PET stands for positron emission tomography. And we talked a few episodes ago about antimatter, and positrons are antimatter. And so what we can do is generate positrons, and when a positron hits another positron, we get the release of huge amounts of energy, and generally in the form of gamma rays. And these lutetium compounds are used in detectors to detect these gamma rays. So if ever you've had a PET scan, you've been close to lutetium. There's a radioactive lutetium isotope, lutetium-177, and that's also used in cancer therapy. And the way that we do this is that you get a small peptide, which is a small molecule made of a few amino acids, and you take this peptide that recognizes certain cancer cells, you then graft the radioactive lutetium isotope to it. It then takes the radioactive lutetium to the cancer cells, and then hopefully the radioactivity of the lutetium then does the trick and kills the cell. In terms of non-medical things, so we use lutetium in catalysts for the cracking of hydrocarbons. That's where you take crude oil straight out of the ground and you essentially sort of distill it, and you end up with hydrocarbons which contain often 8 carbons, which is octane, and they are generally the best for fuel. And we have some important chemical reactions, generally organic reactions, in which lutetium is used as a catalyst. And finally, amongst its uses, there is a compound called lutetium tantalate, which is a lovely name, and it has the formula LuTaO4, and this is the densest known white material. And you might think, wow, okay, so why is that useful? Yeah, I knew you were thinking that. And it, in fact, makes it very, very useful for X-ray detectors. The reason being is that it phosphoresces when it gets hit by X-rays, and so you can see then when the X-rays are coming through.
You did very well finding those boutique uses of lutetium. Give me an interesting fact about it.
Well, this is extraordinarily interesting, actually. Much more interesting than lutetium possibly deserves. But at one stage in the not-too-distant past, lutetium was, in fact, the most expensive metal on the planet.
Really?
I know. The things you find out when you're doing this. It was, in fact, at one stage 6 times more expensive than gold.
Crikey.
I know. So it's still pretty expensive, and it's the most expensive of the lanthanoids, which probably reflects its rarity, but now it's around about a quarter the price of gold. So I hope you didn't invest high and are waiting for it to go higher, because it's not going to.
No, it sounds a bit like the cryptocurrency of the lanthanoids, with this brief and strange explosion in value for no particular reason before subsiding back to its usual obscurity. Okay, short and sweet, that'll do us. Thank you, lutetium. There are lots more lanthanoids in previous episodes of Elemental. Check them out at rnz.co.nz/chemistry or on your favourite podcast app. We're back next time with magnesium. But until then, I'm Alison Balance.
And I'm Allan Blackman. Mā te wā.